So let's do it from fresh, right? Because there is a lot of, I gave this problem because you have to do a balance of problems and theory, because the problems will motivate more theory. Okay. Yeah. But this problem is special in a lot of ways. But I will not try to discuss all of the implications that I know, but let's see. So we have limit n tends to infinity. Yeah, you told me, Chandan. Yeah, right. Yes, Sampal, what were you saying? That is the question that's a very deep question. Okay. And this kind of problem leads to those questions. Under what situations you can exchange and what situations you cannot. You cannot always do it, but you can do it in some situations. But it is difficult to discuss at this point. But in the end, I'll try to say something about it. Okay. Yeah. I mean, that's the thing that is usually proved like at the end of functional analysis course, like after 3 or 4 analysis courses, you learn it, like the proper, there are easier versions of it. But let's come to the problem. Uh-huh. So then you in the end we'll try to discuss like some examples in what cases it works, what cases it doesn't work, and we'll try to make a guess of a theorem. But we will obviously not prove it because we will not obviously prove it. Okay. Let's see. Let's just do this as a problem. So because all of you have tried it and Chandan has an answer, so I would like to Chandan to give us some step by step hints or something like that. Okay. Yeah, that's very clean. Okay. Right. Sorry. Okay. You just take it to the numerator. Okay. Then we'll come down to Sampath's question, exchanging limits, and we'll see. You will see. It will come like that, I think. I'm getting a feeling, but yeah, let's see. Okay. Then you'll do the expansion, geometric series expansion. 1 minute. Yeah, no, but that is an infinite expansion for any n. Okay, because one has to be extremely careful here. Okay, not extremely careful because this is a good situation, but we cannot use a theorem now, so we have to be careful. Okay, so then, wait. Yes. So it will be it's just, so all of you know, this is just a geometric progression. This is just a geometric progression. You don't even need to know the negative binomial expansion or use it. I mean, you know it, but you don't have to do calculations. It's just geometric progression. Okay. How do you integrate it? Yes. So you are splitting the integral, right? But that's not a thing. That's not a theorem, right? See, we always know that integral. So, okay, let me first say what Chandan is doing. So what you are doing, I think, I mean, you can tell me, is 0 to 1 dz and then minus this, right? But you see, integration doesn't, so you are basically exchanging, you're doing the integration first and then doing the addition, subtraction, addition. I mean, that is fine if you have finitely many terms. But if you have infinitely many terms, I just plug in the charger. Okay, if the Wi-Fi goes off, just wait for a second, I'll plug it again. Oh, no, it will not. There is a thing here only. Oh, yes, it will work. 1 second now. So just you guys think this is not something that you can do freely. And it is again a question of exchanging limits and integration. So we will see. This thing. So can anybody, or Chandan, you yourself, can you say how we can, why we can do this? Does it follow from some theorem that this is allowed? So forget about this limit. See, this limit is not the question at all now. Just this part. Yes, yes. Yes, z is a variable from 0 to 1. Yeah, yes. Yes, it is okay to expand it, but it is not okay, or you guys can tell me, to exchange the limit with the addition, right? So what you are doing, and I'm just writing it here, is this thing is equal, but this is not true. You cannot do this. It's not always true. I mean, it's true in this case, it works, and it is okay to do in this case, but you have to say. Oh, because this is not linearity. Linearity means that if you have two terms, then you can split it. All right. So if there are two terms, then you can break it like this. So this is what this is the definition of linearity, that it preserves addition because there are infinitely many terms. Yes. Yes. So that means that for any n, you can do it. See, if you want to prove if you want to extend a result from 2 to n, like you use induction, right? But induction proves never, so induction never proves anything for an infinite set, like in that sense. Induction by induction, this you can do this for all natural numbers n. But doing it for infinitely many at the same time, that you cannot prove by induction. Right. So by induction, you can just get this, that for any n, you can do it. You can do this by induction. But by induction, you try, I mean, how will you prove for infinitely many terms? That is because infinity is not a natural number. Like infinity does not belong to n. There are infinitely many natural numbers, but every natural number is finite. And infinity doesn't belong to it. Okay, so this does not follow from induction, and in fact, it is not true always. You can get strange things. Okay, sometimes you get a lot of correct things. The answer is correct, but the procedure is wrong, and you get wrong answers also many times. Yes, certainly, yeah. So for that, I have to first frame it like what this means in a proper way. What it means to do this in terms of limits. So let's try to understand this. So if we are, let's try to understand. So, okay, let me clean up a few things, you guys think. This is a very delicate matter. Okay? And these things are not hard to prove, but the way we look at functions right now in high school and even in beginning years of college, we look at functions as functions, but we don't look at functions as points. We never take a space of functions. We never consider distance between functions. So that's why it's hard to prove things about functions and sequence of functions. And that's the kind of thing that is happening. But let me at least try to frame what it means to split the thing in a language in which we usually talk about problems in calculus. So if you are doing this, if you have, so just to highlight the thing, I'll write it as functions. And let's say we are doing this. So what it means, like what does it really mean? What it means to do the following. Like, can we put it in terms of something which we, let's see. Okay, that is a verb. That's just a rephrasal, but yeah, not. I'll try to say it. So I'm trying to put it as exchanging limits and integration. I'll try to put it in that language, which is what you asked in the beginning. Okay, and these two are the same questions in the end. We'll try to see. What it means to do the following. Okay. Well, what does this mean? What does it mean? I mean, because it makes no sense to add infinitely many things. So what is it? It is not directly a number, right? It is a number in the end, but to begin with, it's a limit. It's a limit n tends to infinity of, so let me just write it properly. Okay. This is the definition of this summation. Otherwise, it makes no sense to add infinitely many numbers, because infinitely many natural numbers cannot be added, or infinitely many numbers cannot be added at the same time. You can only take limit of them. That's what it means. So you guys are fine with this? Okay. Now, just to condense notation, I will call this Sn. Or no, let's just leave it like this. Okay. Now, what does this mean? Let's write it. Can anybody tell what this means in a similar way of limits and things that I've said? Okay. Yeah. And limit n to infinity, right? Yeah, but I will not even, yeah, that's certainly correct. But you did one extra. No, there's a summation. There's a summation, right? Yeah, okay, so let's do that. Yeah, so it's the same thing. All of you have said the same thing. Sampath like kind of told me the final thing, but I'm not interested in that, like using the fundamental theorems on that. That's not the thing we're interested in. Just anything like this in general can be written in this term. That's all I'm trying to say. So and so yeah, so again, just this like summation. So it's a summation, but finite sums can be exchanged. That's what we're going to use. But let's see. K equal to 1 to n. Once again, just 1 second. Huh? This chair is too high. This was not occupied. That's why I sat here. 1 second. Oh. Sorry, one. Let's change it. Let's change the chair. It's too high with neck pain. Yeah, so it is the summation of these integrals fk x dx. Okay, but this here you can exchange the limit and the summation. I mean the sum and the integral, sorry, yeah, not limit. Here you can exchange the sum and the integral because here we have finitely many things. Now you guys see. Okay, why am I, what am I doing? Yeah, so notation is wrong. That's why I'm getting confused, right? So it is just fk, and then you can take dx. Okay. Now you see, if you just call this sn for a second, then you can see it just becomes a question of exchanging limits and integrals. Maybe snx is maybe the right thing to say, but same thing. That's what this is. I'm not doing anything. I'm just writing things again and again. And the integral. Just exchanging the summation and the integral. That was a question which was asked right at the beginning. And I suppose you guys have, like Adish also said, they have asked it. Yes, applied it, and maybe yeah, he's aware that this question is there. But this thing is the same question. Okay. So at least we know that this question and the initial question are not different. Now, let me not say about in what case we can do and so on. But the problem why we don't understand this thing well, because we see functions in the wrong way for this context. In this context, functions are supposed to be seen as sequences. And so, I mean, sequence of functions, we want to study them in terms of sequences. So functions should be seen like numbers. A function should be seen like numbers. So you should have a concept of distance between functions, space of function. And then you can, I mean, even after, without that also, I can try to say, you can just put layer on layer of terms and do, but then it's not very useful. Uh-huh. This? Yes, I use linearity, but here there are only finitely many terms, so I can do it. No, because I'm doing it for, so I'm doing it for n. Sorry, what? Right. No, so see what so I'll just say this again, and then I think Sampath, you can ask the question again because I didn't understand it very clearly. But let me just say this again. See, what I'm saying is what I have done here is, so this limit n goes to infinity, but n is not infinite. Okay, so n is finite, and then for that finite n, I am exchanging the limit and the summation for this finite n. So I am doing it at each step for finite n. Okay, here it is very different because here it is being done for Sorry. One second. Here it is very different because here it is being done. Sorry, here it is being done for infinitely many terms. So these are different things. Now you can ask your, you should, because I didn't understand it properly. Mm-hmm. Right. Yes. Uh-huh. Right side. Okay. Right side. Yes. Mm-hmm. Mm-hmm. Yeah. Finite subset. Mm-hmm. Yeah. Yeah. They may be different. I mean, this is not equal. We are not saying it is equal. We are just saying what it means for it to be equal. Uh, right. I've actually not done anything. I have not actually proved that this is equal to this. I mean, obviously, understand I've not. Okay, I have basically just written what this means. This means that, these finitely many things we are adding, and then we are taking limits of those finite partial sums, right? But each finite partial sum I can exchange, but actually that does nothing. It doesn't help me to find the answer. Okay, and yeah, right. That's all, yeah. But I have not said that that implies that you can just take limit n to infinity so we can exchange for infinite. No, I'm not saying that. I'm just saying it means this. That's all. Uh, Yes, as long as some, because you can use induction. Induction can prove it for every natural number, but infinity is not. Yeah, right. And this leads to some very deep things about even in graphs, trees. I think once I was discussing trees having finite, finitely many children, each vertex, and then infinite tree, but finite paths. And a lot of things are there, tree induction, and some interesting things. But we're just seeing this, just this, and yeah. But that's not the center. The center of the matter for us is that this question is the same as exchange, whether this thing can be exchanged. So it's not a new question. Once we get conditions, proper conditions under which this can be done, then all of these questions will be answered at once. Okay. Yeah. So Chandan, you see the problem. You also see obviously you see, right? So just take a few minutes and just see if there are anything to ask. Then I'll continue, or maybe just a minute. Yeah, it's really nothing. It's just. So let me not say anything about in what case it can be done, because that will take us in a different direction. Okay, so these two are the same things, but yeah. So there are no questions. Mm-hmm. Mm-hmm. Ah, yes, this one. Hmm. Yeah, we cannot go to the next step as I have written. That's not legal. Yeah, this is not legal. Okay, it is in this case because this functions converge to that thing, but not just converging, they converge in a special way. But yeah, I mean the whole functions actually, the whole functions, I mean these are these are the sequence of functions, partial sum. They converge to this thing, right? This function, or this function, but they do whatever it is, yeah, but they do it in a very special way, like the whole functions themselves converge. So but so as I said, for that we need to see functions as points. That's a good way to understand, but we will not talk about it now. Okay, that is will take us beyond it, then you'll not end up solving this problem. So we cannot do this, but then what can we do? So we have to do something legal. So what can we do? So the answer is half, because in the end, in the end we can do this if we quote the right theorem and if we understand the real matter. But yeah, yeah, and it's not even a power series in that sense because it's 1 by n set there. So, anyways, the answer is half. But yeah, how is it that you can do it? So what I did, I think I went a long way. Okay, I did it a few days back. I did a part of it a few days back, and it's kind of, you have to just try to use integration by parts. Okay, so I will not do the details, but do integration. But please do it. Okay, yeah, integration by parts. Okay, like please work it out. If you do integration by parts, you get half plus, I mean, you will have to play around with some combinations and see which one works. Then you'll get half plus, and it's not hard to believe me. Here, you can just work it out. So you can see, oh, wait. Yes, no, you don't get this. You get a square or something. Okay, so I am not extremely sure about it, but you can see how I get this, right? So you choose this y to the power, you choose this as the integrate, what is, I don't know what it's called, the one that you integrate, and the other you choose the one that you differentiate, and you'll get something like this. I think you'll get exactly this, right? So believe me, this thing. Then basically the job comes down to showing that this limit is something. Okay, so show that this is 0. Okay, show that this is 0. And don't try to use any hi-fi results. You have to just compare this with some function. Okay, that is all you have to do, right? Just compare it with some function and you should be able to do it. Yes, yeah, it is just that, right? I think that works. Yeah. So yeah, something if you compare it, हाँ, फिर वहां से, yeah, you positive वहां से, yeah, हो जाएगा. Okay, but no, you compare this. So you have to compare this function with some function. So if you want to show that this limit is 0, you know it is positive. So you compare it with some other function whose integral you surely know is 0. Okay, and then you will know, right? So you just compare it with y to the, yeah, some kind of squeezing. And squeezing is fine because those are properties of integrals which we know. Integral is, yeah, you can explain that. Okay, but the first day when I was doing this, I got here and I got stuck. I was like, what is, I was just, mind was blocked, not working. So I was trying to write this in terms of some other special functions, harmonic functions, hypergeometry series. I was getting more and more confused. Okay, but then today evening I was trying, and then suddenly it good, simple. Okay, so that's it. So what did we learn here? Well, that you have to try things like integration by parts and so on. I mean, you have to try things basically. And then the key thing is that most often when you have to prove, I mean, see, especially in high school level, I mean, or even basic exams, whatever, this is from that perspective. You have to basically compare functions. Okay, and in general, you will see a lot of problems like this in tomato and so on, even in other. I mean, when you have to prove some integral inequalities, You don't have to usually use some high-fi inequalities usually what if there is some inequalities between integrals and some corresponding functions, you have to usually first set up a relation between the functions and then you have to do. That's not always the case, obviously, but I have seen this several times. Okay, but yeah, that's just sorry. Uh-huh. Haha, वो भी that is basically the derivative method, right? To ah yeah, so you would usually know if you have to do that kind of this time or just try them. So we're just talking about this is just the tricks of the trade. Okay, not so interesting for general things, but usually this is the things, right? That if you have to show that some integral is positive, then you try to, interpret this as a function or something, function of t, and then you check its derivative, and mm, those are just some computation, not very, yeah. And this is not that topic, and it's not okay. You can do that, or you can. So why do you need to take y square? This is what? No, this is false. Yes, the other way, and that's what you need. And yes, and then you integrate. Yeah, or you can don't even need this. You can just say this. This works. Okay, right. So it is fine. So it's good to cheat and and apply the geometric expansion, and you get the answer as half, and then you would know that this is going to be zero. Okay, so then you can prove it easily. Mm, yes. So maybe just as a small homework, you guys can. This is very easy, I suppose. Um, okay, okay, okay. So you can share it with me or share it with everyone. Just share it with me. I'll share it with everyone. Oh, then yeah, now only we can do it. Yeah. It's just okay. Wait. 1/n square. कहाँ से कहाँ तक? Oh, okay. Okay. So this is homework. Okay. Okay. Don't say. Yeah. Okay. Fine. Given. So okay. Okay. So try to figure this out. Okay. This is half saying, and also, but it's a much simpler question that I'm giving. You can think about this also. Yeah, you can take this t and limit. No, what am I doing? Sorry. Array. Once again, so this is t to limit. I'm not defining these things. You can take the definition that you know. This is like an improper integral, but you can think. Just try to think and see. 1 over x dx. Find. Find or show it doesn't exist. You won't need Riemann integral theory. Just some kind of boundedness or something. So, okay. And this is obviously there. So these two problems try. Note it down. Let's go to the. Okay, Sampath, you have a question? Anyone has questions? Hmm. Yes, but even to state it, yeah, so let's try to see. So if you have, so I'll just say it in this case only. So if you have this fnx 0 to 1, that doesn't matter, dx, and this is limit n goes to infinity, obviously, right? And we want, and this is a very good thing to know, at least, if not prove it. If you want to exchange the limit and the integral, and you're asking what case can this be done? Well, so if for each x in the interval, that this is a very obvious thing to ask. If for each x in 0, 1, this sequence, or maybe for each f x naught, this sequence, this limit exists, this is the first condition. Condition 1, if this happens, this has to happen first, okay? If for every x naught, so this is a function, but for every x naught, you get an actual sequence of numbers, if this limit exists, okay? That's the first condition. Okay, before I move to the second condition, is this condition satisfied in our question? In our question, fnx is nx to the power n minus 1 by 1 plus x. So does for every x is the limit defined? So you see the answer is no, because at x equal to 1, what you get is n by 2. And the limit of this as n goes to infinity does not exist. Okay. So for x not equal to 1, this sequence of values fn1 doesn't converge. So that's why we cannot exchange. And you can see if you exchange, you'll get the wrong answer. Okay, you'll get 0. If you just exchange it here, I think you get 0. You can see that. Yes, so in this condition, you do have to take 1, because you can see at 1, I think, yes, you have to include the limits. That's what I'm doing here, that I think you have to include. Now, there may be some other generalization and so on, I don't know, but this is at least the case, okay? That in this case, you take. So you see that this at 1, this limit doesn't exist, okay? This is called pointwise convergence, okay? There, I remember some essay question in which there was this question on sequence of functions converging. Don't remember. I'll probably make it up, but have to take some time, some similar question. But let me state the next condition. This is the first condition. And the second condition is that all of fnx is dominated, and this is a word used, it's very important, is dominated by some g for all. So there is a g, there is another function which kind of is above all of the fnx for each x. That's what this means, that for each n, for all n, for all x, it happens. So there is some kind of a, upper cover, and you have this other condition. Then that implies, and hopefully I'm not wrong, that you can do this. Then you can exchange. No, just think. For each x, you need that to happen. And for all n also, right? I mean, 1g for every n. It is not so obvious that this can always be done. Right. You see, right? Like for all n, there should be a g. That like the one g should work for all the n's. Infinitely many functions, infinitely many values also. So it's not obvious that, yeah. You can already see this theorem is like a top class theorem. I mean, it requires a lot of maturity to even like, yeah, I don't have much intuition for this. And I don't think it's very intuitive as well. I mean, in a simple sense. So otherwise, as you said, you can just take Fn only, Fn plus one. So there are a lot of subtle things I want us to understand before, like this pointwise convergence, uniform boundary. There's a lot of things out there. Some deep things about which basically, though these theorems basically being theorems implies that we don't understand real numbers that well. That's why these are theorems and not obvious things. Okay, it comes later. So, but this is called the dominated convergence theorem. Okay, dominated convergence theorem. But yeah, but you can always use this. You can always, if you're going to if you're going to exchange limits, you can always check if these conditions are not satisfied, then you better not exchange. Okay, like that is not what this is saying. It is saying that if these conditions are satisfied, then you can do it. Okay, but it is such a strong theorem that if this condition is not satisfied, then you better not. This is a very strong theorem. I don't think it is so easy to prove. No. It is only sufficient, but usually it is also necessary, and because it's such a strong result. Okay, it is not hard to prove, but the language needs to be different. We need to go to what are called measures and so on. But yeah, we'll not see that at all. It's way down the line. There are some simple conditions under which it can be exchanged, but let me not say it. But those are actually more cumbersome to state. Okay. So yeah. I will put in some questions related to these things. Like I'll give some functions and ask, is there a g such that it can happen, and pointwise, so on. Okay, there are a lot of elementary questions can be asked. Yes. Yeah. But for x2 and it works, right? Yes, and x, and also it can be exchanged. I guess you can check something like that, right? Yeah. So you see, it works. So if you yeah, so this is a good thing which I should do. I mean, it's good to do here. X raised to n, you see, for x raised to n, for every x naught, definitely this happens, right? Because I mean 0 to 1. If x is strictly less than 1, then obviously the limit is 0. You put an x naught which is less than 1, take powers, it goes to 0. When you take x equal to 1, it suddenly goes to 1, but that's fine. It's still, the limit still exists, right? 1, 1, 1, 1, so that's 1. Okay, for every x naught between 0 to 1, it's fine. It exists. And obviously it is dominated because you can just take x itself, x raised to the n, and you can take x plus 1. So now this theorem tells you that you can exchange these things. And you see, you don't get the wrong answer, I hope. Otherwise you can catch me. Otherwise what I'm saying is wrong. So, but you see, this is n goes to infinity. Okay. This limit, and this limit is 0. Wait, what am I saying? Yeah, this limit is 0, right? Yeah, it's fine. I mean, here it's fine. You can you can take it. Yeah, but you can catch me there. You can say that x can be 1 also. So actually the limit is not 0. This limit is, it's 0, but then only at 1 it is 1. So it is a function, the limit is a function g, which is 0 for x less than 1 and is 1 for x equal to 1, but it's fine. Iska bhi integral 0 yoga. The value 1 doesn't matter in the integration, that you know. The value at 1 doesn't matter in the integration, so it's fine. So you can understand, it works. Okay. Yeah, so let me do this clearly, because I think I've rushed this. Let me just do this. Let me write this clearly, then you guys can think. And so what we are trying to do is trying to check this theorem, whether this theorem works or not in some cases where we can actually find the value ourselves, and then we can use this theorem and see if this gives the right result or not. Okay, so first let us check this in this problem itself. Okay, so see, in this problem, a limit exchange does not work, because if you exchange, so if you exchange, let's do this. Let's try to see, since we have already stated this, we should try to get used to it a little bit. This thing, so you can see that this limit is equal to 0, right? You take any y, it is 0, right? So let me write this clearly. So now you take fn y, okay, you take fn y equal to ny to the power this. Okay, so now if we take limit fn y n tends to infinity, what is this? So let's first, you guys think about this. Okay, so I'm exchanging and then I'm trying to see what happens. Does something go wrong or not? So what does it mean to say limit of this function? Just for every y, you tell me the limit. Right? So it is equal to, so it will be a function. So what you have to do, you have to just pick some y and find the limit. Right? So you put a y naught. And you take the limit. This limit is 0, right? If y naught is not equal, if y naught is less than 1. So that's why it will be 0 if y naught is less than 1. Is everybody comfortable with this? Is it fine? Okay. Chandan, Rasuvro, is this okay? I am taking the limit for every y. Okay, good. Thanks. I'm taking the limit for every y. Okay. And then I'm checking. Now, as Adish said, for 1, and you guys can see this, for 1, it is not. What is the limit for y not equal to 1? It is infinite. Because of y not equal to 1, you can see something happens, which is not 0. It's not, it's n over 2. It's infinite. Okay. But what will be the integral of this function? So now we have a function which we want to integrate, right? And what is that function? That function is function which is 0 for y naught less than 1, and it is infinite for y naught equal to 1. Let us say infinity is allowed and so on. Let's say. But even then, the integral of this function you see, we have to integrate this only, right? Because this thing is now this strange function. After taking the limit, it becomes a piecewise function, kind of, if you want to call it piecewise. But this is still 0, because you know that the end point, that's just the point in the end, that doesn't really matter for the integration, right? Yes, if you go very strictly with the definition, then that's true. Maybe but the definition, yeah, that's I mean, then I can just say that this function, this limit does not exist. I mean, this function, nobody can't even say. No, yeah, that's right. But in this case, but you guys see that you will surely not get half. right? I mean, this is surely not half. No, it doesn't. No, it doesn't go to infinity. It is actually infinity itself. Yes, yes. Yeah, it doesn't. Yeah, you can just ignore it. Yes. Right. See, if I want to put it very precisely, I have to say that we are integrating gx not from 0 to 1 because at 1 it is not defined. Then I have to just say that you are integrating it from 0 to t, where t goes to 1. And you see, this is going to be 0 because t is never 1 now. Okay, then it's the limit of zeros. For every t, it is 0, and the limit of zeros as t goes to 1 is going to be 0. Whatever t goes to doesn't matter. It's a limit of zeros, okay, for every t. So I have to say like, but you can understand. I mean, just one point doesn't matter. If you go with the in the exact definition, also see when we take the partition, we take the minimum and maximum inside the partition strictly, not on the boundary values. Okay, but yeah, let's not. Yeah, but we know it's not half, and you can say it's 0 by this argument. So that's wrong. You see, exchanging, we are clearly seeing that exchanging limits and integrals does not give us the right answer. And also you can see that condition 1 is not satisfied. So also 1 is not satisfied. Okay, try to see this. You can see this here only. So what is condition 1? For every x naught, we want the limit to exist. For every y naught, you want the limit to exist. But for y naught equal to 1, the limit is infinite. Because it's n by 2 ka limit, n by 2, yeah, 1 by 2, 2 by 2, 3 by 2. That is the sequence. So is it okay? Yes. Yes, because it matters because these are fn's are actually some continuous functions. So it will affect the things. Okay, not continuous, they are something else, but we can just say some functions where it matters. They are measurable functions. Yes, yes, but yeah, but so does everybody see that it doesn't work in this? Like in this case, we cannot exchange the limits and integrals, and this theorem has kind of already warned you that you cannot because condition 1 is not satisfied. Okay, now let us look at a positive result, which is x to the n. Let us see. Second, so let's go there. Yeah, so then let's me erase this thing completely. Keep the theorem there. Density. So today we got a little bit of comfortable with sequence of functions. So we can do problems with that. And obviously there is theory for that, but we won't do much theory of that now in this core thing preparation. We can do it in other classes. Let's see. So if you look at, now you look at fn x equal to x raised to the n and see, let's do it carefully. Something is, and we want to that's fn x. Now you guys tell me, how can you use this theorem to say that you can exchange the limit with the integral? So this one you guys do, means Try to tell me. Right. So tell me carefully here. So limit n tend to infinity fnx for what point? No, for x. So this is just clear. All of you know, understand this. So what does it say? That condition 1 is satisfied. Okay. Now, how is condition 2 satisfied? Yeah, you can say I should put an equal to actually, but it's fine. You can just say x plus 1 also if I don't put equal to. So that is clear. Exact. This is true for every n and every x. This one thing works. Okay. So this theorem tells you that you can exchange. So we can exchange. Just writing exchange. That's all we are exchanging today. So what do we get when we exchange? So you guys tell me, what do you get when you exchange? Yes. So we get 0, but also let me say this carefully. This becomes a function gx, right? Where g, so because for every x you're taking the limit, right? So you'll get a function for every x, the limit that is for the limit at x naught for this thing will be g of x naught and so on. So this, what is this function g? All of you know, but g of x naught. Yes, g. So this g of x naught is 0 when x naught is less than 1, right? And g of x naught is 1 at x naught equal to 1. That's what the g is. That's what we have written here, right? So the g is nothing but the limit. Yeah, it is the limit of fn x naught or x10 to the power x naught, same thing. It is a limit. That's what g of x naught is, right? So now for such a function, which is 0 for all x between 0 to 1, and just except for 1, this is obviously this integral is 0. No doubt, right? So you're looking at this function, which is 0, and then at 1, it is 1. This integral is obviously 0. And this is the correct answer, right? Because even if you do it by hand, without any theorem, you get x to the n plus 1 by n plus 1, right? Then you do the integration, you get 1 by n plus 1. Then you take the limit, you get 0. So matches. So this theorem is working in this case. This theorem gives an answer, but also you can check it directly. So any questions? Because today I'll just end at this. Yeah, I'll not say anything more today. So then if there are no questions, then today we'll stop. Okay, I started late. Usually this will not happen. Usually this doesn't happen. You start at 9:30 only. Today, okay. So yeah, it's already pretty late here. So we'll stop here today, I think, for you guys also. So yeah, that's it. Any questions? So the problems that I gave, the two other problems, discuss, think about them, and yeah, just do the problems from the sources you have. And some people are writing the mock test, those who are preparing. Others, and others, if you want to write, anyone can write, obviously, the test. But yeah, that's what depends. And yeah, next time I will do more problems. Maybe in between, maybe I'll send a few problems, which is just based on area of sets, which doesn't use integration, but area of sets. I will ask some questions where you have to use some combination of maybe combinatorial type of reasoning and some limit type of reasoning mixed. And yes, yes, we can do that. Yes, we can do that. So let me do that next week, definitely. Yeah. So basically, invariance principle kind of question. So basically, where you want to prove that something cannot be done. So there is some process going